So hello, this is Nicolo. In this video I will show you how to install Salome Meca 2019 in the operating system Ubuntu 20.04. So this is Ubuntu focal fossa, and I want to first acknowledge the sources where I took the information to create this video. So first of all, the Codaster forum. So this is the Codaster website. It has a forum, and you can find a lot of information here. And then there are YouTube video which are great from made by Cyprien Russo. There is one about open source FEA, how to install Salome Meca 2017, which is great, but the reason I made this video is because this procedure doesn't work straight away anymore in the new version. And then there are two more videos where you can see Salome Meca 2017 tutorial, simple plate linear static analysis, which teach you how to go through the interface of Salome Meca and creating a simple analysis. And then another shorter video about extracting stress result. And all these videos are by Cyprien Russo. So the reason why I made this video, I say this because if you try to install it on Ubuntu 20.04, you will have some problem. So I'm going to show you the installation from scratch, and then I'm also using it, so I will go through an example. So first of all, I wrote all the instructions that I'm telling you now on a file that I will put in the comments or in the description of the video. First of all, you go to the Codaster web page. Okay, you can just Google Codaster, code minus aster, or just insert this URL, and you will find the home page of the Codaster. And then you go to the download section. Okay, the download section has several options on the left. So in this case we are not installing Codaster alone, but the entire package Salome Meca. Okay, and I pick the version 2019. Okay, because that's the one I know it works, and it can also be parallelized, but this will not be covered in this video. So if you click on Salome Meca 2019, you can save the file. Because it's a big file, I already saved it. Okay, it's already downloaded for me. So I have this file in my download folder, Salome Meca. It's a .tgz file. It's an archive. Okay. So next step is I create an installation directory. So it's in my project directory. It will be called Salome Meca 2019. You can do that from the terminal, or just do that from the Ubuntu interface. So I go to Home Project, right click, new folder, Salome Meca 2018. Okay, I created my my folder. Okay, now I go in the download, I cut the archive, and I put it here. So I have my Salome Meca here. And then if I go back to the web page, first thing, there are some prerequisites. I'm not sure which one of these prerequisites are necessary, because some of these are just for compiling from source. Okay. However, it's better safe than sorry, so I'm gonna show you how to install all of them. Okay. First of all, open a shell. So open the terminal. So it's Ctrl-Alt-T. Okay, and my shell appears. And I want to make a very short digression. In my case, you see there is a parenthesis on the left of my terminal. So there is the name of my computer, latitude. Okay, and then there is a parenthesis which is written mouse in this case. This is a conda environment. So if you just installed your operating system, you will not have a conda environment. So just skip this part because it's not relevant. However, this is an environment which manages some packages which may interfere with the installation. I'm sure they do interfere with if you try to compile codaster from source, but in any case it's better to remove this conda environment. You could just deactivate it using conda deactivate, okay, but this just you just switch the behavior from a specific conda package to the base, but we want to actually deactivate completely the conda package. So what I do is to vim bashrc. Okay, if you don't know what is vim, it's a text editor, just check it out yourself. So the bashrc is the file that is executed at the beginning, and there is a specific place where you find the conda environment. In my case it's because I have a Moose framework installation, and in this case I need to comment this line, so I introduce the comment of this part of the bashrc. Okay. So you comment everything, so from the export path to the mini conda, and then you comment all the conda setup and unset conda setup and the conda activate. Okay, everything is commented now, and it appears as light blue. Okay, then you save the file. Okay, just double Z in Vim, and then once you do this modification, you have to reopen the shell. Okay, so now Ctrl-Alt-T, I reopen the shell. Now you see it's a normal shell. There is no more parentheses on the left hand side, so there is no more conda environment. Okay. However, as I said, if your installation, if your Ubuntu installation is just new, you don't need to care about this part, so just skip, because you will not have any conda environment. If you don't know, just check in your bashrc file. If you haven't installed the conda on purpose for some software, you will not have it. So good. So second thing, we go to the prerequisite. If you go to the codaster page, download prerequisite, there are a series of packages which are needed, and this one they can be installed from terminal. In the instruction I wrote, there are a few more of these packages. Okay, and the reason is because I was following some other instructions which are relevant for compiling codaster from source, but that's not what we are doing in this video. So there are these prerequisites, and the very first thing you should check, as they say, it's Python. Okay, Python is required. Normally they suggest you to install 3.6, but in my case, because the Ubuntu 20.04 has its own Python version which is greater than 3.6, normally you don't need to care about Python, but I'm just showing you what you need to check. So first you do Python -- version in the terminal, and you see I have 2.7. okay, and then you do Python 3 -- version, I have 3.8. So in my case the prerequisites are already satisfied. Okay, I have the right Python. Okay. However, in the unlucky case that you don't have it, you need to install it. Okay, and here I provide you instruction to do so. So if Python 3 is not present, you need to run this command, which I'm not running now, but I just show you which one they are, because otherwise it will not do anything for me. So sudo add-apt-repository ppa :deadsnakes /ppa. Okay, this one add the repository to your list of repository, and then the second command is sudo apt-get update. Okay, it's for updating your packages, and then sudo apt-get install Python 3.6. okay, so if you run this and you did not have Python 3, then you should get this one installed, and it's fine. There may be an unlucky case in which you have a Python, for instance 3.4, so it's not enough for the Salome Meca, but at the same time yeah, you have 3 in the sense that you have maybe 3.4, but is not updated, so it's not the required one, which was 3.6. In this case you need to be careful. So if you install Python 3.6 with these 3 commands, so add repository, update, and then install Python 3.6, it's fine, but then the command Python 3, you will see that if you do minus version, it will remain the one that was before, because you cannot, if you install a new version of Python, Ubuntu will have 2 versions of Python, but you are not modifying the command Python 3. Okay, the way to do so, the way to get Python 3 pointing correctly to the right version of Python is to create a virtual environment. Okay, so first of all you need to install the development package. This one was a package that was required. It's not really related with the virtual environment, but it's something I forgot to do. So sudo apt-get install Python 3.6 -dev. Okay, and then you can create the virtual environment. So you can open, for instance, the shell inside the Salome Meca folder. So right click, open terminal. Okay, and then you do this one. So sudo apt-get update. I'm not doing this now because in my case I already have the version of Python. So sudo apt-get update, and then sudo apt-get install Python 3 -virtualenv. Okay, this will install the virtual environment, and then you have to launch the virtual environment. Okay, like this, virtualenv -p us, and you point to the Python 3.6 in your usr bin folder, and then venv. After you do this, so as I said, imagine you have a version like Python 3.4 and you install 3.6. After you create the virtual environment, Python 3 version will not point anymore to the original version that was in Ubuntu, but it will point to the 3.6. So at this point you are fine. Okay, but as I said before, if you already have, like me, a version of Python which should be the one that is currently installed in Ubuntu by default 3.8, you don't need to care about all these instructions. So you just skip the instruction from the install Python 3.6 until the end of the virtual environment. Okay, this is for the Python. So the requirements are this one. You need to install these packages. As I said, some of these packages are in the Codaster website. Some they were in another link which was related with the Codaster installation from source. Just install all of them. There is nothing bad that can happen. So the way you install them is, for instance, sudo apt-get install gcc, for instance, which is the compiler. So if I run this, it asks me my password, and then it just tells me that there are no I'm already at the most recent version, because before I installed all these packages myself. But if you did not, just go through all this command and install all the necessary packages. Okay, once you have done this, now we have all the prerequisites. Okay, all the prerequisites are satisfied. So now we uncompress the archive. So we are in the folder Salome Meca, and you can see the archive. And then what you do is this one. So tar xvf and the name of the archive. Okay, so I'm extracting this. Since it's a big archive, so it may take a bit actually. So let's see. And you see, as soon as you extract it, you will get one more file which is called Salome Meca 2019 universal.run. Okay. So this is taking a bit, so I'm pausing the video and I will restart the video when this is finished. So I'm back here. Now the extraction has taken place. It was really like maybe 40 seconds or something like this. It was pretty quick. So now we have this universal.run. We can cancel the other one because it's just the same thing. It's just the extracted version. We can empty the bin. Okay. So now that you have this installer, you have to run it as an executable. So again, you have your terminal in the folder and this / the name of the executable, so Salome Meca 2019. Okay, I'm gonna run it now. And so as soon as I run, it's self-extracting. Okay, enter the installation directory. So the default is in my home folder, but I don't want it in my home folder, but I want it inside here, so inside this project Salome Meca. So I'm gonna tell it just install there. Okay, so I put home Nicolo project Salome Meca 2018. Okay, and it's gonna extract it there. Do you want to be in French? No, I want in English. So you click N and enter, and then the installation start. Again, this one may take maybe a bit, so I'm gonna pause the video again. I'm back here. So it took exactly 7 minutes for me to make the installation. There are a couple of warnings saying that a directory is in a path variable but does not exist. Don't worry, these one are not critical for the functioning of the software. So finally you will see just these few messages. Okay, so now it's installed. If you go to the Ubuntu search and you search Salome, okay, yeah, you see the icon. So you can launch the program just by clicking on this icon, or another way to launch it is to go with the terminal in the so you see you will have created this apply v 2019 0.3 universal. So cd apply, okay, this one, okay, and then there is an executable. You see there is a Salome executable. So if you do /Salome, okay, this will just execute the program for you. Okay, so now it's starting. Now what I want to show you are the problem you face when you actually start it. Okay, because now it looks installed, but you will see that you cannot just use it as it is. So this one is the interface. The first thing I also, this one at the same time I give you an example of how to build a simple geometry like a cube and make a tensile test simulation. So first you want to go in the geometry. Okay, now I click geometry, and then when I click on geometry, yeah, that's you get the first fatal error. Okay, you see it tells you OpenGL window, create window, context fail. This is related to the OpenGL, and you cannot go on. This one is a fatal error, and actually it gets pretty stuck. I'm not. You need to go here and just impose to the yeah, you see it's a bit buggy. So in this case, what to do is to search for just to kill it from the shell. And in this case, if you kill it from the shell, it will just stop. But if you have launched it from this command line, it will a bit get stuck, and you will need to kill the process manually. So this is the first problem. So how to solve this problem? Well, this problem is already known. It's in a specific page. So I give you the link of the forum where I found the solution. So I copy the link, then I paste it on my browser. There is a solution written here, but I'm not going to go through this, but I give you the solution. So the problem is a standard C++ library which is inside the Salome Meca folder, and specifically you have to do control directory to this folder. So you see this folder is in Salome Meca 2019 v 2019.0.3 universal prerequisite Debian for Salome lib. Okay, so if you list the file here, you see there is this lib std C++. So this is the standard library in C++. Now the point is one of these doesn't work properly. So what you need to do is to remove it. Okay, so this is done by the command. So rm libstd c++.so.s.6. Okay, this is the one that you need to remove. Okay, now you see it's not there anymore. Okay, but then you need to add one, and what you do is not copying one but linking one. So you have a link command. So just a brief explanation of what this means. ln is a link command. It means you link. You create a file which is a symbolic link to another file. So the actual file that you are using is in usr lib x86 linux gnu libstd c++.so.6. Okay, it's the same as before. And then you link it into a file called in the same way, but inside the Salome Meca folder. So if you click enter, then if you list, you see that you have this one. So now you have the file again. It looks like the same file as before, but it's not, because you have removed it. This one is a link. Is a link to a file which is in the operating system. So usr lib, which is the folder where the operating system keeps the library. Okay. So once you have done this, you go back. You go again in the application folder. It's called apply. Yeah, this one, and I launch again Salome. Okay. Okay. Now we are back. We are back to Salome. Now let's go again to build the geometry. Alright, now you see it works great. You see the axis. Okay, so this is the solution to the first problem, which was not present in the 2017 version or in previous operating system. Alright, so I build a simple geometry. This is also somehow a tutorial on how to build a geometry. So I want a cube. I click on the cube, size 200, fine. I have a box. Okay, you see the box. Then I need to create faces for my boundary condition. So I want to apply simple tension to this cube. So you go to new entity, group, create group. Okay, the group is gonna be face. We call it, for instance, left. It's the left index coordinate. We take it from box 1. Now we need to select it. So I need to rotate it because I want the face which is in the negative x. Okay, so I think you rotate with this. You see, you click on this rotation. Okay, and then you can rotate the geometry. Okay. And finally I want to select this face. You see, you can do show only selected. Okay, and it's gonna show you the face that you selected. And then you edit. You click on it, you edit, and then apply and close. Okay. This is one face. Then you go back to the box view. You close the face view and you go back to the box view. Now I want to select the face in the negative y. Okay, this one. Okay, so new entity, group, create group. This one I call it bottom, and I'm gonna select it. So box 1. Okay, show only selected. Okay, you need to specify that is a face. Bottom, box 1, then click show only selected. You see this face here. You select again, add. Okay, and then apply and close, and you created another surface. Then you go back to the box view. Now I want to create a surface in the negative z, so z equal to 0. This one. new entity, group, create group, face, I call it the back, okay, and then box 1, I click on that, add, then show only selected, you see, it's the negative Z, apply and close. Then the final one I want to define is in the positive Z, where I want to apply the load. Okay, the other 3 surfaces will be blocked perpendicular to their normal. Now in the positive Z I want to create the surface with the load, so create group, face, I call it front. Okay, here I want box 1, you click on box 1 right when you want it, then you select this one, add, show only selected, this is the positive Z, apply and close. Alright, cancel the view, put the box view. Okay, now you created your dimension. It's always a good idea to save from time to time, so you can save your file as an HDF file. I prefer to save it inside the Salome Meca folder, so this one is gonna be my example cube file. Okay, save. Alright, then geometry is done. Now we go to create a mesh. Okay, let's wait a moment. So we're gonna create a very simple mesh, so we can see the box, and then okay, let me see. So you do mesh, create mesh, exactly, yeah, create mesh. It's called mesh 1, geometry is box 1. Now we need to assign the type, so it's going to be an hexaedral, then assign a set of hypotheses, 3D automatic. Okay, it's going to ask you how many segments you want for each direction. I'm just going to put 2, so it will have 8 elements in total. Okay, click OK. Algorithm is going to be hexaedron, fine. No hypothesis. Okay, at this point you apply and close. Okay, and you've got this one, you see they are the hypothesis that you put, the algorithm used, and the mesh. Okay, so at this point you can cancel the box view and apply the mesh view, at this point, so first, sorry, you need to calculate the mesh, compute, sorry, it's called the compute. So after you create the mesh, you need to compute it. Okay, and it tells you, okay, I generated 8 elements. Okay, fine, you see your 8 elements. These are applied hypothesis, algorithm, etc. Okay, only just close it, and only box 1 will remain red. So fine, we save it again. Nice. Now at this point you need to create the aster study. So this one is for defining the material and the load, etc. Before that, I think I need to define the group again for the boundary condition. So you have defined the group for the faces, but this is the geometry. Now I'm defining a group of element, of faces of element for the boundary condition. So you do create mesh, create group. Alright, I call them the same as I call in the geometry. So there will be left, which is the negative x. It's going to be a face, group on geometry. Okay, and then you can pick from the geometry. Yeah, you can. You click here, direct geometry selection, and you click here on the left. Okay. So basically, I'm telling that there is a face called the left on the mesh that corresponds to the left in the geometry. Okay, apply and close. You have to do the same for all of them. Create group. Mesh is going to be the mesh 1. It's going to be a face. It's going to be called the bottom. Group on geometry. Direct import, so bottom. So now I'm telling bottom is bottom, so the bottom part is the bottom element. Okay, apply and close. Now mesh again, create group. I pick the mesh again, is mesh 1. It's a face. It's gonna be called back. I select from the direct geometry selection back. So I'm saying mesh 1 back is back. Okay. final one, mesh, create group. Again, mesh is mesh one. It's a face. It's gonna be called front, and it's gonna correspond to the geometric group called front. Okay, so mesh one, face, front is front. Okay, all right. We have all of them defined for the boundary condition. Now save it. Now we want to go to the aster study. Okay, now let's see when I click aster study to define the material and boundary condition, etc. It's a bit slowing down. Let's see what happens. All right, be patient, wait a moment. I'm gonna pause the video a moment. So we're back here. So what happened is that it got stuck for maybe 30-40 seconds, and then it's gonna tell me failed to activate module aster study. This is a fatal error. You cannot go on. So luckily we saved our work until now. If you write OK, it's just it brings you back to the mesh. So you cannot go on from this. Again, this is another problem that was not present in the 2017 video by Cyprian. What you need to do is while you saved, close aster. Are you sure you want to quit? Yes. So there is a workaround for this. The point is the module for aster study will not be found. So this has been discussed in this page in the forum. So you can see yourself the solution here, but I'm going to tell you. There is a missing package, which is a libffi6, which you can download from this package. If you don't have this link, you can Google libffi6 for Debian, and you're gonna find this particular package. So in this case, I copy the link. I put the link in my browser, and that's the direct download page. So, I save my file. Okay, downloaded. This is a pretty small file. It doesn't matter. So you open the download folder. This is a .deb file. So I just cut and paste it in my Salome Meca. You can just click on enter on that because this is a Debian installation file. Okay. So this is just gonna open the Ubuntu Software Center. Okay, Ubuntu Software Center is telling me this package exists. Is foreign function interface library runtime. You install it. Okay, it's gonna ask you the password. All right. So once this one is installed, you will not have anymore the problem with the codaster study module not found. So this was the trick to solve this problem that was not present in the previous version. Okay. So it's pretty quick to install, just a few seconds. Okay, you can remove it later if you don't need it anymore. But you know, you need to keep it until you use this version of Salome Meca. Okay, so I close the software center. Now again, I go back to my shell. I launch Salome again. Now luckily I saved my progress, so I'm gonna restart from the point where I was. So you open, then it's gonna bring you in another folder. But if you go to the project, my project folder, then Salome, I have the example cube. You just open it and it brings you back to the point I was. Here you need to, when you open a file, you need to again click on geometry, otherwise it doesn't show you the geometry. And then you click again on mesh, and it opens another window with the mesh. You see, these are the windows. You can switch from the geometry window to the mesh window, and then you click on the little eye here. You can see again your mesh. Okay. So now let's go to the aster study, where we can define all our material property. I stuck a bit again, but now it starts. You see, please wait, and then now great, it starts. So just because we installed this libffi, now everything is working fine. So case view, current case. So how to do this? I think you need to right click on this, right click on current stage, add stage, which is the same as a simulation step, basically. It's one load step. Okay, so we have stage 1. Now you click on the mesh, you read a mesh, okay, because we need to tell that in this step we use this particular mesh. Name fine mesh is gonna use the mesh one that we see before. The format is gonna be MED, the standard one. There is no other option to click here, so it's fine. This one I want to mention, this problem. So you're supposed, every time you click one of these, you're supposed to click an OK button, which is below. Maybe there's a problem with my screen, I don't know, but it's annoying. You see, basically the window is higher, is taller than my screen, and I couldn't find a simple way to resize it. It's not easy. You can, even if you click this one, it doesn't really resize. So what I do is you click Alt, you keep pressing Alt and F7, click 1 F7. You see now the cursor becomes a little end, okay, and you can pull the window up, okay, and then you see it appear, the bottom appears. You see now there is apply, close, okay. You just need to click on apply, okay, and then okay, just the same. But now every time you will see my little end appearing, it means I'm clicking Alt, so I keep pressing Alt and F7. And then you see I can transport my window around. I don't know if it's just me or it's a common problem, but now I give you the workaround, right? So the mesh is read, fine. Now we need model definition, assign a finite element, okay. So the name can be model, is fine. You need to, so the mesh is gonna be mesh, fine. This one you need to click on finite element, I think, and then you need to add an item. You edit it, and you need to say that you apply the same model everywhere, fine. That's it's pretty much standard. And then the phenomenon is a mechanic. We want to do the mechanic, and then you add a modelization, which is 3D, okay. So everywhere mechanic 3D, and then you're gonna go down and click on OK. Alright, then it's gonna, the finite element is done, mesh is done. These options are not important for us, okay. So now the model is done, okay. Now that the model is done, you go to the material, okay. You need to define a material first. Alright, so we will go really basic. We call it matter, linear isotropic. We hopefully in another video I will show you how to do plasticity and crystal plasticity, but this time we are just about Young modulus. So I put 200 gigapascal, so I keep a megapascal unit, 0.3 Poisson ratio, so easy. Okay. Now it should be done, I think. Yeah, we edited the property. Yeah, okay again. Okay, so my material is defined. So this information box is the one that will appear in the input file. Actually, is the log of the input file. So now we have defined a material, but we need to assign it. So we need to tell that the geometry is made of this material, because you can have many, right? You can have different material in one geometry. So it's called the field math. We want to assign it to the model. Okay, so its model is going to be this one, and then you add an item in the material assignment, you need to edit it, so you want it everywhere in this model, and the material is gonna be matter. Okay, so that's it. Okay, in the model, everywhere, yes. Okay, fine. This one has assigned the material. Okay, now it's assigned, so the material is done. Now function and list are not important for us. Boundary condition, of course, we need them. Assign mechanical load. Okay, so name is called load. Okay, fine. Face info, this one is just because I'm just interested in displacement boundary condition, so I just click on face info, and then you need to add the item. So the first item is gonna be, you need to check which group of element you want. On the let me see, group of element. I thought they were appearing here. Let me see, possibly I'm doing something wrong. Let's cancel this one for a moment. So if I apply the x equal to 0, yeah, for some reason I must have made some mistake. My element, the faces are not here, which should be. So let's go back a moment, because I think I may have made some mistake when I imported the mesh, maybe. Just 1 second. So we save it a moment. Then cancel. Yes, I want to cancel this procedure. This one is cancel this one again. Yes. So let's go back 1 moment, because I think either when I assigned the mesh, it was no, because for some reason the mesh was not assigned properly. Mesh 1. Yeah, you have to be careful that when you are in the mesh assignment, the mesh is the name that you gave in the mesh module before. Okay, now let's check it now. So I modified this one, then I go back to the load. Now let's see, face info, so displacement boundary condition. Now let's see if the group of elements are found. Yes, now you see the group of elements are found, so I pick the left one, so you see it gets highlighted, so it's the negative x. I click OK, and then the x equal to 0. I want it to be blocked along the x direction. Alright, okay. Now I'm supposed to add another one. Let's try to click OK again. Okay, now I'm back. So you need to add one condition for each element. You need to add another one and then edit it. So for instance, now I pick bottom, and bottom is going to be blocked along y, so dy is the displacement y equal to 0. Okay. Now I add another one. It's going to be for back. Okay, that's going to be blocked along z, so no displacement z. And then a final one is going to be on front. Okay, front, so positive x. Okay, the x this time I put a number like 1. Okay, so the formation is 1 and the length is 200. Okay, so I have my 4 boundary condition. Now it's okay. I click OK. Alright, this is the boundary condition. Then I think pre-analysis, we don't need anything. It can't be restored in graphical mode. Strange. I don't know why there was this warning. Anyway, analysis, we do static mechanical. Okay, that's what we want to do. we need to pick the structural, no, sorry, the material field, I think, or the structural element. No, it's material field. So this one is called the wrestling. Okay, it's the standard name of the analysis. So material field is this one. The model is model, and then the load, we need to add which load we want to use, and they are the one called the load. No other option are needed here. So I think we've got everything for this wrestling. Okay, so this is the analysis. It's called the wrestling. And then post-processing is for adding some field, so the field that will be in output. It's called the calc champ, so calculate the field. The name, you need to use the same as before, so call it wrestling. You must use the same as the analysis, otherwise the paravis viewer will not find your field. So wrestling. We want to calculate constraint, so these are the stresses. The useful one, I recommend use CIF ELGA. This one are it's related to the stress component in the Gaussian point. ELGA stands for Gaussian point, and the sigma ELGA. You need both to get the component of the stress and also the invariance, like the phomesis stress. Result is wrestling. Okay, the important thing is this name wrestling is the same as here when you do the post-processing. Yes, this one I think it's fine. And then criteria is the one for getting the von Mises. You need to put the same as before, so is the, I think, the sig ELGA. I'm not gonna go through the detail of this. Put ELGA and ELNO. ELNO are for the node, and then ELGA is for the Gauss point. CIF ELNO. Okay, and then I add sigma ELNO. Okay, so ELGA, ELNO, CIF sigma, and this one I think the invariance you want sig, so they are the stress invariant, ELGA and ELNO. So it means Mises, Tresca, stress, etc. Result is wrestling. Okay, that's it. Okay, so the post-process should be fine now. Fracture and fatigue we don't want. Then output. Okay, we need to set output result. We need to give a location for the file. So it's gonna be my file, and it's gonna be called example cube and dot. They are always .med file. Okay, .med is the format. Example cube.med. So check it, just extend this and check that your file is correct. .med. Then your format is med, is the standard. And then it's asking, you need to add one result, so you need to tell that you want wrestling. Okay, you have only one, you have two of them, but I think if they are called with the same name, you don't need to export both. I think if you call with different name, then you need to export both, but in this case it should be sufficient. So wrestling statical mechanics. Okay, alright, so okay, there should be everything. So example cube med result. Okay, so the output is done. At this point I think everything is done. Now I'm gonna save it. So all the Aster study are done. Now to run the simulation, you click here history view. Okay, and you see there is current case and the stage 1. You need to click the plus here. Okay, so you enable the run, and then you go at the bottom of the page and there is a run button. Okay, so hopefully it ran. I hope I did everything correctly. you need to refresh. You see this hourglass rotating. You need to refresh sometimes to see the messages. And I think it may have been yeah. If you see the green, it means it's successful, and this one is the log. It will return 0 at the end. So it tells you how much time it takes, and if the return is 0, you see address 0, it means it's fine, it's gone. Okay, now this simulation is done. So Codaster is installed, and you can run simulation, build the model. To see the result, you go back to the case view, and you will have this file. So data files. So data files means the one that are in the folder. You see in the folder now you get a .med. It appears like a music file in my computer, but it's the output. Okay. Now let's go back to Salome. Now you right click on this. Right click on in the data files, example cube, open in Paravis. Okay. Now it's embedded in the graphical interface. So it's gonna now it's stuck a bit, but it's gonna open finally. Let's see. Yes, this one is Paravis. So Paravis is just the same as Paraview, but it's embedded. This one is my little cube. You can see already the displacement. See if I can find I can't see the color bar. Must be somewhere. So here there are all the options. If you're familiar with Paraview, it's pretty obvious what they are. But right now I just, the only thing I cannot see is the legend. So the color bar actually. So you can edit the color bar. Maybe show idea. Okay, it was hidden for some reason. So if you click this one, you see this one is coloring, means is the option of the color bar. You can edit your option. There are a lot of different way to change the label, etc. This one is the displacement. So if you go wrestling depth, you can see displacement. So you can see I have deformed along Z, and the deformation amplitude is 1. Okay, you see it's deformed along Z. I don't know if you can see properly the axis in this video. So Z is along this, and then there is lateral contraction, and you see it's minus 0.3 because the Poisson ratio was 0.3, and same in the X direction. Okay, lateral. Okay, nice. And the faces that were blocked, they are blocked. To see the stress that you output with the post processor, you need to use the filter. So Paravis has filter like Paraview. So filters, I think you need to use the cell data to point data. Let's see what happens. Now you should have no, sorry, first you need to enable just 1 moment. So example cube, cancel this one. You need to go in the property tab. Okay, property tab, you can see all the sigma, sig, this one. So you activate by ticking everything. You apply. Okay, now they are enabled, so you can see them, but you still cannot see them here. I mean, they look like constant value. You need to do filter, cell data to point data, apply, and then you can see them interpolate. Let me see. Maybe that was not the right way. Just give me a second. I think probably the filter was not the right one. Okay, I apply. Let me see. There is data to point data. Yeah, they are this one. Sorry, they are the field to surface. There are specific filters which are developed for Codaster. They are called Elga field to surface. So let's try this one. Yeah, now I can see them. Yeah, this one is the stress. Yeah, you see it's uniform stress, and then there are the component. So sigma xx, because the boundary is free, it's very small. Okay, then yy, zz, the shear stress is not present. So the important one is the zz is 1000. You see 1000 because the young modulus was 200 gigapascal, so 200,000 multiplied by the strain, which is 1 over 200, so it gives 1000. Okay, if you calculate with the young modulus I used, this is correct. And then you can see in the this is the sigma. So sigma gives the component, and then sif again the component. I think sic, yeah, siec is the one that gives the equivalent. So you have von Mises, in this case it's trivial, it's 1000. You have Tresca 1000 again. Principal stress, there are two of them which are 0, and the third one is 1000. That's it. The other are all equivalent stress. So that's it. This is the tutorial. We've got Salome Meca 2018 installed on Ubuntu 20. We've got a brief tutorial on how to use it. Sorry for the mistakes, but I hope you can appreciate this video. And all the instructions are written in this file that I'm gonna put in the description of the video. Okay. So thank you for watching, and hope now you can run easily Salome Meca 2018 on the newest Ubuntu. Thank you for watching.